I'm going to now hand over to Mauro to present on the limit equilibrium analysis. So this is a sort of introductory presentation on that, and it fits into session 2, methods of slope stability analysis. And we have 2 sessions on limit equilibrium, and he's going to talk to that a little bit later as well. So 2 perspectives. But Mauro, if you can share your slides and then run through them from your screen, over to you.
Okay, good. Okay, so please let me know, Andrew, and if you have any problems seeing or hearing my voice. So my topic here will be to talk about limit equilibrium analysis. And the presentation I divided here into, let me see if these slides are moving. Here we go, okay. So yeah, I try to talk here on this presentation about kind of an overview on limit equilibrium analysis, and then talk a little bit about some of the instances or situations where you can find some problems or limitations of the method, and that we all should be aware of this when using limit equilibrium analysis to calculate the factor of safety of our structures. So the whole point of the method is to come up with what we call the factor of safety, and that is the relationship between the shear strength and the mobilizing shear stress on the failure surface. And that's a very important part of our projects. I think you all acknowledge that. And the factor of safety is the factor by which the shear strength of the soil needs to be reduced so the potential failure surface comes to a state of limit equilibrium. That's the whole concept. And the method's been there for many, many years. And how we do this is to divide the potential failure surface into slices. And we take the equations of equilibrium in the base of those slices. So you can calculate the force equilibrium, you can calculate the moment equilibrium on the base of each of those slices. And originally in the publications, if you go back to the work done by Morgenstern and Spencer and others in the 60s and 50s, people were calculating factor safeties using the circular slip surfaces, but now I think there's many softwares around that can allow you to calculate more complex failure surfaces, such as composite or even fully specified. You can specify a failure surface and can calculate the factor safety on the base of those failure surfaces as well. One important aspect is that the limit equilibrium analysis, there's an assumption behind it, and we should be aware of that, because that's a very important assumption, that the factor of safety is the same for all the slices on the base of all the slices, and that's not the case in reality, as the factor of safety is different on the base of each single portion of a failure surface. I'm going to talk about that in more detail in the presentation. So in essence, what the method does, and as I said, it's been there for many, many years, and it was important to solve many problems in the past, is to divide a potential failure surface into many, many slices, and you take the equations on the base of those slices. So you look at a shear force that's mobilizing the slice in the base of those slices. You look at the shear strength of the soil. You look at the normal force. You can add tension cracks. You can add surface loads. And if you look into all those forces and do a equilibrium calculation, you can look into horizontal equilibrium, you can do moment equilibrium, and you can come up with the factor of safety for the whole slip surface and see what is the relationship between the shear strength of those soils and the shear stress that's mobilizing that surface. And in the original publications, people were working with circular slip surface. You can do the same thing if you're working with composite or fully specified slip surface. The problem's the same. Some new variables arise when you now work with circular slip surface. It's pretty much the same approach, so it doesn't change that much. And it's pretty straightforward to do. What we do when you take those forces is to calculate the factor of safety, and you can do that with respect to moment equilibrium and also with respect to horizontal force equilibrium. And the problem with this equation is that you cannot calculate those equations if you don't have an assumption, one or two assumptions to calculate those equations, because you have way too many variables here. And the factor of safety depends on the normal force on the base of the slice, and the normal force depends on the factor of safety. So you have a statically indeterminate equation where you have more variables than equations to solve. So you have to come up with some assumptions. And the first methods, they came up with the assumption that the shear force, the intra-slice shear force was zero. That means that you don't have shear between different slices, you just have slices that don't have like contact between them, and that simplifies the equation a lot. And the more complex methods, they have assumptions to calculate the intra-slice shear force, and they all follow this very simple equation here, where we have a function, and you can use different functions for that. And the intra-slice shear force and the normal shear force, they vary based on that function and on this lambda as well. And what we do with those methods, such as Morgenstern Price and Spencer, is to actually change that lambda and over a certain number of interactions, and the moment equilibrium equation will reach the same value as the force equilibrium. And at that position, you have what they call the factor of safety. So the factor of safety for the more rigorous methods, such as Morgenstern Price and Spencer, it is actually where the force and moment equilibrium can give you the same value for the factor of safety. And those equations, they'll reach the same response. If you take lambda to be equal to zero, that means you don't have any intra-slice shear forces. And that is simplification that was used by Bishop and Yambu with those methods. The difference between them is that Bishop only solved the moment equilibrium and Yambu only solved the force equilibrium. So there's many methods out there, and the difference between them is whether they are solving for moment equilibrium or force equilibrium. That changes. Many authors have different approaches to this. And what is the assumption they use for the intra-slice shear forces? If they include the shear forces, if they don't, and how they handle this process. I think in practice now, we have come to a point where people just use the more rigorous methods. They usually use the Morgenstern Price or Spencer method. In Brazil, for instance, we have some regulations that require people to use 3 of those methods. So sometimes people would use Spencer, Morgenstern, and maybe Bishop's as well. But it's not necessary that it is a regulation we have here in place. But to be honest, you shouldn't have that. I mean, if you're calculating for Morgenstern Price, Spencer, it should be good. It should be fine, as those are the most rigorous method, and they solve for both force equilibrium and moment equilibrium as well. Okay, talking about some of the limitations or some things you should be aware of when using the linear equilibrium method. One important thing is that if you solve the equation for linear equilibrium, there's an assumption behind it that the factor of safety is the same for the entire slip surface, and that's not the case in reality. And what I did here to show this is to take an upstream tailings dam, and I use here a pocket of material that I said, oh, this material is assumed to be a liquefiable material, so that could be a liquefiable tailings, and it is saturated, it's behind the water table. So I use here the peak and drain shear strength, and we talked about that extensively yesterday. And I came up with the factor of safety 1.3 in limited ribbon. And then I went into the sigma stress approach in GeoStudio, and I calculated the in situ shear stresses in the soil, in the tailings, and looked into the local factor of safety. So if you take in the base of each of those slices, you can see what is the shear stress that's mobilizing the slice, the shear strength as well, and see what the factor of safety is. And you're going to see you have a region here where that pocket of material is, where the factor of safety is below 1. So the driving shear stress is exceeding the yield undrained shear strength, which means that that material is mobilizing shear stress that it cannot handle with the peak shear strength. And I went on to change that to the liquefied strength, assuming that the pocket of material could have liquefied. And if you do that, the factor of safety is 0.96. So this is an example just to show that the factor of safety 1.3 may not be sufficient to handle a liquefaction, even for a small pocket of material, a small portion of the material. I'm not assuming the whole material liquefied, just this very low pocket here, and it was not sufficient for that case. And I'm not going to talk extensively about that. You're going to have classes about the bulletin 194, and there's some guidances on that document as how to handle and how to design TSS that has contracted materials in the structural zones of the TSF. One second point of attention, and that was highlighted by Steve Wright in his 2013 Bolton Seed lecture. That is available on YouTube. I have the link here for those of you who do not have seen this before. It's a very interesting lecture where he talks about some situations he ran into and had problems with his low stability analysis. And one of those cases was he was calculating the factor of safety for this structure, and he came up with the factor of safety 0.56. And he was like, well, what is that? And then when he looked into the failure surface, there's tension in the failure surface, meaning that the shear strength in that portion is actually mobilizing the failure surface instead of resisting the movement. So be aware that when you have materials, cohesion materials, and low effective stress, sometimes that can happen. And the real factor of safety for this case is 2.57 instead of 0.56. So always check for the effective stresses that you're considering in your calculation. That's a very important aspect. I've had that problem one time. That made me remember one problem I was running in the past. And it was actually doing a drawdown analysis when you reduce very rapidly the water in the reservoir, because you have a very high reduce in total stress, and sometimes you maintain the poor water pressures. So you reduce the effective stress very quickly, and that can lead to tension as well. And I reproduced that problem here. It was not the same geometry I had problems with in the past, but just to try to show one more example, I reproduced that example in the slide. And I noticed in the new version, they don't give you that problem anymore, because they have they exclude the failure surfaces that have tension in it. So apparently you should be fine now, but in the old version of the slide, they wouldn't do that. They would consider this failure surface, and they would have a very low factor of safety. I actually had to go into the slide and find some buttons there to find this slip surface, because it wasn't giving me this slip surface in the first trial. Apparently they do not consider this anymore, but there's some ways you can unlock that slip surface in slide if you look for it. That's a very important point, so be aware of that. Always look for tension and make sure you don't have tension in the failure surface. One problem, a paper I found very interesting in tailings and mine waste in 2020, and that was by a colleague, Hugo Brandão. He's now living in Australia, and he looked into this problem of a TSF that had a contractive material in the foundation, and he was designing this structure and using circular slip surface, and it was giving him a factor of safety 1.5. And then he ran the FLAC with strain reduction and got a factor of safety very slow, I think 1.2 or something. The FLAC was 1.26. And he started to look with the optimized slip surface, what the optimized slip surface would do, and if he was able to capture this more sophisticated slip surface going through this weak material. I'm not sure if you guys can see on the screen, but you're going to see you have a black continuous line, and you have a dashed line as well. Those are a circular slip surface in GeoStudio in slide. And you have the FLAC strain rate here going through the material, which is the slip surface the FLAC was given. And the optimized slip surface for this case, when he used it, the optimized slip surface, it was able to capture that more complex movement, more complex slip surface. So I insert this slide here with I think it's a very interesting application of the optimization, but be aware that's not always the case. There's many instances where the optimization can give you very weird slip surfaces that you should not consider those. So I don't think that's a common approach. Some people don't like the optimization. I myself like to see the results, what they give me, especially when I have more contractive materials at the foundation. But be aware that can give you some slip surfaces that you shouldn't consider in your analysis as well. For this particular case, the optimization was able to get a factor of safety very close to what he was finding with the FLAC analysis. And this, I think, that's the last point on the presentation. Just a very brief comment on 3D and 2D. And that's a very interesting seed lecture as well, was given by Professor Von Griffiths. He took this slope, the very interesting example. He took on the slope, very simple example, and he put one very soft material going through the slope, and he took the factor of safety 3D and found it to be 1.52. And then he went on to calculate a factor, 2D factors of safety throughout the entire slope, going from left to right, and he plotted this curve here. And he was basically making the point that 2D is not always more conservative than 3D. Some people would have that assumption that 2D would yield a lower factor of safety than 3D. And it actually depends on where you take that cross section. If you take that cross section in the abutment, the factor of safety 2D would be higher than the factor of safety, the 3D factor of safety. But if you take in the middle portion, and the fact then you're on what he called the safe side, where the factor of safety on 2D is below the 3D. The degree of conservatism of the 2D factor of safety, it depends a lot on the location of the cross section. So that's a very important point when you're choosing your cross section. Make sure you choose it on a region where you're gonna have a higher shear stresses or elevated phreatic surface or higher embankment to calculate your factor of safety. I think that's a pretty standard procedure for people working on design. But it's always important to highlight that and understand that the location of the cross section is very important. Okay, so my last slide here, some closing remarks. Limb equilibrium analysis has been there for many years. In fact, it is 880 years since the ordinary methods or Fellaini's methods were created. I think that was in 1936 or something. In the original intent of the publications, it was developed for circular slip surfaces and with some relatively simple stratigraphy and pore water pressure conditions. And now we're making it more and more complicated. So the equations are the same, but the conditions now we can do many more things that was intended to do in the past. With the computers and softwares, I think we now can evaluate many complex structures. And as I pointed out in the presentation, you can evaluate fully specified slip surfaces, circular slip surface, and all kinds. The factor safety equations, you can't calculate those equations if you don't have certain assumptions into it. So that's what leads to many methods as to what the as to what equations of equilibrium are being solved and what is the assumption in terms of interlight shear forces. The more rigorous methods, such as Morgenstern, Price, and Spencer, are being used today, and I think it will continue to be as they are the ones that solve both moment equilibrium and force equilibrium. It is important to remember that the factor safety is the same along the entire slip surface when you use a limit equilibrium analysis, and that may not be realistic. So there's ways to more sophisticated analysis and numerical models that you can evaluate that further. And always check the effective stress and hydraulic gradient of the materials of interest to avoid tension in the base of those lights. As I am aware now, I think the softwares do not allow you to have tension anymore, because I think they will ignore that slip surface. But I mean, do your homework. Look at the base of look at the slip surface. Make sure you're not considering negative shear stresses. Make sure the hydraulic gradients are within certain limits, so you don't have problems with the pore pressure in your analysis. I think that's all for me, and I'll be around here if you guys have questions.
Oh, thanks very much, Mauro. We appreciate that, and certainly it shows that two different people can do the same analysis and get different answers depending on how you analyze it and whether you know what slip circle you use and whether you optimize it. So very useful insight as to how we do those types of analyses. And Mauro, thanks very much for joining us at early hours of the morning in Brazil. I'm not quite sure whether it's 4 or 5 in the morning or something, but we appreciate
your
time. 4 o'clock, okay.
That's good.
We are scheduled to have a break now, but Andy Small, I'm wondering whether we shouldn't just do your presentation now, and then it's a 15-minute sort of slot, and then take a break. Is that convenient for you?
That would be fine, Andrew. Yes.
All right. I'm going to hand over to you, and if you can bring up the next presentation, or if you can share, if you can share your slides. Thank you. And he's going to talk to us about the pseudo-static and dynamic slope stability.
Yeah, I believe I'm sharing my presentation screen, Andrew. Andrew, are you seeing the correct screen?
To put it into presentation mode.
Yes, I shall. But just okay there.
That's great. Thank you.
Okay. Before I start this presentation, I'd like to comment on Mauro's presentation. There's a paper that Andrew, I sent to you that I'd like to distribute to the participants. Mechanism of failure of the Mount Polley Tailing Storage Facility. This was written in the Canadian Geotechnical Journal by Elena Zabalutny, Nordy Morgenstern Award Wilson. And this is one of the biggest case studies that Nordy refers to as to the limitations of limit equilibrium analyses. As Mauro said, the factor safety is the same at the bottom of each slice, and it doesn't address the stress strain behavior of the different materials that may comprise the dam. Mount Poly is a very good case study of having 3 or 4 different materials with very different stress strain behaviors, and how the limit equilibrium could not pick up at all the way that a true slope, the dam would truly perform. And so this paper goes through the finite element calculations and limit equilibrium, and shows how some zones had exceeded their peak strength and were headed towards residual, while other zones hadn't got to their peak strength yet. So it's a very important paper. So whenever you hear Nordy Morgenstern talking about the limitations of limit equilibrium, this is one of his key concerns, and that's why he's been advocating for performance-based design. So on that note, I'm going to flip over to the presentation I was planning to give you on pseudo-static analyses and simplified deformation analyses. I'm just going to touch on some of the basics. It's only about 25 slides. We're going to talk about some of the basics and limitations of pseudo-static, the Heinz-Griffin-Franklin procedure, the seismic coefficient, and some of the shear strengths to be used. We're fundamentally moving away from this analysis as it is misunderstood, misused, and of limited value. SANCOLD clearly says pseudo-static isn't in the toolbox anymore. At ICOLD, we're not as hard on that, but we are saying you need to be careful when you use it and use it properly. And even these days, we see many misuses of this analysis all around the world. So the focus of this presentation is to address misunderstandings and misuses of pseudo-static analyses. Pseudo-static analysis is one of the earliest forms of analysis for seismic stability, where they took a block on a sliding plane, had a weight, and it applied a force that represented the horizontal force due to an earthquake. And with these forces, then they calculated factor safety of that sliding block. Heinz, Griffin, and Franklin developed a very comprehensive approach for pseudostatic analysis in 1984, and this is often cited as a key reference document for pseudostatic analyses. And they say in that document that dams with adequate static factors of safety against sliding are not likely to be predicted by this analysis to be subject to deformations so large as to endanger the reservoirs, though limited sliding may be predicted. So this was developed based on a number of case studies for water dams. I think it's over 350 case studies. And they looked at the seismic performance of these 350 water dams. And they used a threshold of 1 meter, believing that if you had more than 1 meter of deformation on a water dam, then that could endanger the reservoir. So their whole process was geared towards establishing factor of safety, which would tell you whether or not there'd be more than 1 meter of settlement or deformations. Many of our tailings facilities can take much more than 1 meter of deformation. So you heard in the earlier remarks by Andrew some of the differences between water dams and tailings dams. This is another thing we have to be careful of, taking water dam experience into our tailings dam world. And so then what was happening is people were calculating a pseudostatic factor safety of a greater than or less than 1, and then saying the dam could fail during an earthquake, when that was not the intention of the pseudostatic analyses. It's simply a simplified deformation analysis. It's a surrogate. The other piece is that pseudostatic analysis should not be used if you have a significant strength loss. So many of our tailings facilities have contractive tailings, particularly in the upstream portion. Even centerline constructed tailings dams, I've seen pseudostatic analyses run with the slip surfaces through the contractile and liquefiable tailings and calculating a pseudostatic analysis. Well, that's fundamentally flawed. It's wrong. So you need to assess the liquefaction susceptibility and cyclic softening potential of the soils before you do a pseudostatic, or even the simplified deformation analyses I'll touch on in a moment. So coming back to Heinz, Griffin, and Franklin, they said if you take the peak ground acceleration at the bedrock and multiply it by 0.5, put it into a stability model, and come up with a factor of safety of 1, then it would be unlikely to have more than 1 meter of deformation. And note their statement. The authors have arbitrarily chosen 1 meter of permanent displacement as a tolerable upper limit. Such a deformation would surely be considered serious damage. Well, this is water dams, not tailings dams. They talk about 80% of the shear strength, and we've seen many people take pseudostatic analyses, and they take the phi of 30 degrees, take 80% of that to call it 24 degrees, run the analysis. But when you read Heinz Griffin closely and you read some of the supporting literature, what they were talking about was 80% of the undrained shear strength, not of the drained shear strength. And so this is part of the misunderstandings in pseudostatic. And fundamentally, if you have a dilative soil with a friction angle of 30 degrees, Duncan and Wright have said that you really don't need to discount the drain strength. That during a seismic event, there will be some deformations occur within the dam. And as you heard yesterday, such deformations on dilative soils can actually lead to negative pore water pressures, which actually lead to an increase in undrained strength. And then you may have pore pressures generated by virtue of the earthquake. The two offset each other. And at the end of the day, Duncan and Wright says you do not actually need to discount the drain strength. So fundamentally, don't apply the 0.8 factor. Now, if we have contractive materials that do not liquefy or strain soften, and this comes into what Paul is going to be showing later of what we have in Appendix B of the ICOLD bulletin, then what I do in my practice is I do a test assuming undrained shear strength, a peak undrained shear strength. If it passes there, that's fine. I then take a look at the seismic event and say, yeah, maybe it could cause cyclic softening, maybe it couldn't. If I get a factor safety greater than 1, then I'm okay. But if I get a factor safety of less than 1, that doesn't mean we have a problem. Because when you take the undrained shear strength, you're already assuming a lot of pore pressure generation. So again, I do this if a regulator says I need to check a box to do pseudostatic analysis. I then write a story in my reports that try to explain why pseudostatic analyses are flawed and that they're not appropriate. We need to change these regulatory requirements we have all around the world that call for pseudostatic analysis. So it may provide an indication of potential deformation, use with caution, but fundamentally use these other approaches. We've evolved substantially over the years and don't need to rely on pseudostatic analyses. I've talked a bit about that already. So there's a number of different simplified methods. There's a Newmark method, which is very simple, Magnesian seed. But really, the state of practice is Bray and Travesaro's or Bray and Macedo's work, which takes the slope movement as a flexible block. It uses a nonlinear soil response with fully coupled sliding block models. It's been calibrated against 650 measured ground motions, and you can use it in probabilistic or deterministic frameworks. So I provide some information in this paper on Heinz and Griffin Franklin approaches. If you need to use it, fine. We're not advocating for it, so I'm going to skip past that. So Bray and Traversaro did a lot of work in 2007 and 2017 on a simplified procedure for estimating shear-induced permanent displacement for shallow crustal earthquakes and for subduction earthquakes. I have a website link I'll be sharing with you in a moment that provides very good information. It provides the research papers that Bray has produced on these topics and looks at the different types of earthquakes that could lead to deformations. And they have provided a spreadsheet to help you with that. It helps you calculate the displacements for these different earthquake zones. So it was initially developed in 2007. It can be used to determine the probability of achieving a zero displacement, and it can provide estimated displacements. Jorge Macedo and Jonathan Bray then updated the work in 2019. At the end of this presentation, I have a series of references, including the specific references to these papers. So I revert to the spreadsheet calculation that's provided by Bray. This is the website, and on that website is the spreadsheet. This is linked to the spreadsheet. You need the average shear wave velocity of the sliding mass, which many projects now have with seismic cone penetration testing. The yield coefficient, this is a bit of a challenge because you actually need to do pseudo-static analyses in effect to find the yield coefficient, which is the coefficient which gives a factor safety of 1, the earthquake magnitude, and then the spectral acceleration of a specific time period. With that information, you can use that spreadsheet. But we need to understand that this is giving some indication of deformations, which isn't necessarily just crest settlement. And then extending these deformations to crest settlement is a bit of a challenge. And we need to look closer at the sliding block mechanisms. It's not clear how that all works. So as a screening exercise, we often will say that the deformations that were obtained from these analyses are providing vertical deformations. Really, they're providing a non-vertical deformation, but you would have to resolve it to get the vertical deformation. But if you assume those deformations are vertical and you can live with them, then you're done. But if you need to go beyond that, there's ways to do it. If your crest settlement is close to available freeboard, simplified methods may not be adequate. So for some of my projects where they are water dams, they are tailings dams, water dams, that are supporting water covers over acid generating tailings, I do have challenges with freeboard, and we do have to be careful of that. These types of methods aren't appropriate. We need to be moving into more advanced methods with nonlinear deformation analyses. But if you have a tailings dam, centerline or downstream construction, or even it can't be upstream because liquefaction is a problem. But if you're centerline or downstream construction, very robust, you don't have a lot of internal drainage elements which are deformation sensitive, and you're dealing with 3, 5, or 10 meters of freeboard, then this approach can be just fine. This one is another tool I use that can be done in 5 minutes. This is a Swaysgood 2003. They developed a simplified approach based on 69 case studies, and they provide the formula here and how to do it. This is a very simple spreadsheet. It gives me an indication of the potential settlement. Am I into centimeters or decimeters of movement? But obviously the preferred approach is getting into nonlinear deformation analyses. They use the appropriate constitutive models, and you're going to be seeing more on that later today. So when we're dealing with seismic deformation, we need to start with the liquefaction assessment. If the tailings or any elements within the dam can liquefy, then you're driven to use limit equilibrium with post-earthquake stability analyses. And that may tell you the factor safety is greater than 1.1, and you say, okay, fine, we can tolerate that. But really, it's the deformations that matter. And even if your factor safety greater than 1.1, you should still look at doing a deformation analyses if you're getting close to 1.1 or 1.2, just to be sure that the deformations are adequate and acceptable to you. But if you're less than 1.1, the deformation analysis is nearly a must. So I think that's what we're seeing, that last point. So the last slide, for any earthquake ground motion, we can get the spectral acceleration. You should know the spectral period, the site conditions, the shear wave velocities. You would use the seismic design event based on the consequence classification or your design criteria. And sometimes simplified methods are good enough. Sometimes you need to draw the FLAC analysis, need to do the dynamic FLAC analysis, and I spoke a bit about that. And we have to keep in mind deformation is hard to predict. Use these analyses to inform your engineering judgment. So an example, I have a dam that's only 15 meters high. We subjected it to a magnitude 7 earthquake, calculated 10 to 15 centimeters of settlement. During a major flood event, our flood routing is showing us that during the flood, I could have 40 centimeters of settlement. My seismic, my simplified deformation analyses are saying 10 to 15 centimeters. During the flood, though, I may have 40 centimeters. Do I have enough freeboard? I'm saying maybe not. Just because the math is telling me I'm okay, I still need to use judgment to say, look, that's getting close to some thresholds. I need to be careful. And so therefore I'm treating that as a credible failure mode, even though the math is telling me it may not happen. So as we say here, use your judgment. At the end of this presentation, I've included a series of references here, which there's the Ray Macedo work. Yeah, so I think this there's lots of good papers on this, lots of good guidance, lots of good information on how to do it properly. If you're going to use pseudostatic, do it carefully and try to explain to the world why we shouldn't be doing it.